and we're going to talk about Merkle-CRDTs as a way to replicate data between peers in a peer-to-peer network. But more importantly, than understanding how they exactly work, is that you leave this talk with some ideas of things you can potentially do on top of the IPFS DAG. First things first, my name is Hector Sanjuan. I work at Protocol Labs as a software engineer. Together with some colleagues, Samoli, Pedro, Yanis, we put together this Merkle-CRDT paper a couple of years ago. The paper is not difficult and has long introductions to a lot of the concepts that we rely on, but of course you don't need to have read the paper to follow through this presentation, but just know it's there in case you want to read it later. I put a picture of my avatar there, not because I look extremely pretty in it, but because of the background. The designer decided to put some castles in it, even though they didn't know that I love castles, so I find it magnificent. And in the IPFS ecosystem, we have different types of bricks and modules and tech that can be combined into something bigger, so that you can say that today I'm essentially going to be building a castle. Because a castle is a structure built by putting some things on top of other things in a way that it doesn't fall and crumble. So my castle has the property that it can store things and form a network with other castles to replicate the storage. I promise there will be more cool pictures. But what we're building in modern terms is a replicated key value store. A key value store is essentially a table with 3 operations: get, put, and list, read, write, and query. My replicating key value store is special in that it has some non-trivial properties, so some things that are not super easy to get when you're implementing something distributed like this. In this case, all participant replicas of this table can write to the table at any time. All replicas can join, can leave at any time and in any number. Anything can happen to the messages on the network. They can be dropped, they can be reordered, they can be corrupted. Despite all of these, things eventually in time converge. So all replicas which have will have exactly the same key value store with the same elements and the same values when they have applied exactly the same messages. The key here as well is that I'm going to do all of this with little effort. And in order to do that, I'm going to need some solid foundations. If you build something with a solid foundation, this happens. You see that tower? This was a tower in Zaragoza, Spain. The finish was pretty nice. It was awesome. It looked beautiful. The foundations were not so good. Have you seen this tower before? Has anyone seen this tower before? Why not? Because it's not there anymore. They had to they had to take it out. It had to be dismantled. Therefore, I'm going to use some very solid foundations for what I want to build so that I don't have to dismantle my towers. Okay. The first foundation is libp2p. There we go. The first foundation is libp2p gossips app. As you know, libp2p allows me to create a peer-to-peer network, and gossips app is a scalable PubSub implementation that allows every peer in the network to broadcast messages to others. This is using Falcon and is quite solid these days. The second foundation is IPLD. IPLD is a number of interoperable formats to create content-addressed blocks and links between them to form Merkle DAGs. And a Merkle DAG is like a tree in which every node is content-addressed. So it is interested not only because of all the properties of content-addressed data, but because once I traverse one of these Merkle DAGs and I'm done with it, I will never have to traverse it again because it cannot change. As in, it's going to be essentially content address and immutable, which allows me to actually not doing something twice. The third foundation is IPFS. IPFS allows us to make our IPLD nodes available to a peer-to-peer network, providing them to other participants and retrieving them from other participants when needed, using content routing and peer routing. So that means IPFS allow us to replicate the Merkle DAGs that I'm building with IPLD. And the fourth piece is CRDTs. Conflict-free replicated data types allow us to modify a shared state, so a state that is common to other participants in a network without coordination or centralized conflict resolution. This logo for CRDTs was generated using Stable Diffusion, and it was the best it could come up with. So now we have the building blocks, and we can start building. Allow me to switch to witches iconography from castles, because it's also good. I find it very beautiful. In my cauldron, I'm going to put a P2P host. I'm going to put some PubSub leaves and a fresh IPFS instance. All of these are things that are available in your forest or from your local IPFS implementer. And the parts that need some witchcraft will be the CRDT parts. So first is the CRDT part, so the part where I need to implement a key value stored using a conflict-free data type. There are different families of CRDTs, but in this case we can use an operation-based CRDT. Operation-based CRDT allow conflict-free concurrent modification of a state by specifying that the operations used to modify that state must always be commutative. So the order in which they are applied is irrelevant, and the result in our replicas will always be the same. We can implement our key value store rather simply. Instead of having a single table where we add and we delete, what we're going to do is to have two tables, an elements table for added keys and a tombstone table for deleted keys. Additionally, every key is going to have a unique ID. And this way, we're going to avoid conflicts when multiple replicas add or delete the same key at the same time, since they will have what are seemingly random IDs. Therefore, the replica will append a unique ID and a priority when it receives a write operation and broadcast that to the others. When an operation is received, the elements table and the tombstone table in case of deletes are updated accordingly. What is the process of checking if a key exists? If a key has been added to my tables, we check that the elements table for all the elements that have that key and verify that at least one of them is not in the tombstone table. That means that they have not been deleted, not that we may have several entries in the elements table with the same key but different IDs. So the process of deleting a key is that we get all those elements for the same key with all their different IDs and put all of them in the tombstones table. In CRDT jargon, this is an add wins observed removed set. But additionally, since this is not a set but a key value store, we are going to need two more tables, one with the current value of a key and one with the current priority of a key. So when we write a key, we can use priority to determine if the new value of that key should overwrite what we already have. And if priority is the same, we can always resolve the conflict, for example, by alphabetically sorting the values, but never randomly. So always the conflict resolution needs to happen in exactly the same way in every place and need to be the same result. The priority can be a number, can be potentially a timestamp, anything that helps you decide which key should have priority over the others. So as you can see, this is conflict-free. Replicas do their operations. Anyone receiving those operations can apply them, regardless of the order. And eventually, they all come to the same state. They will answer the get questions, the list questions in exactly the same way. But note that for all replicas to converge, it is important that they receive all the operations. And operation-based CRDTs have the problem that normally they require reliable message delivery. So because otherwise things don't converge. If one message is lost, you will never come to the place where you want to get. Therefore, if you don't have reliable message delivery, which really you never have, you need to re-implement strategies to ensure that your messages are delivered. Therefore, you need to track which messages you have delivered, which you have not delivered, etc. Things start getting very complicated very fast. The second part of the CRDT work that we're doing with our witchery help us deal with that by taking advantage of our foundations. This is the Merkle-CRDT part. Rather than just broadcasting our CRDT operations, as we will do in a normal implementation of operation CRDTs, what we're going to do is to add each operation to a Merkle DAG, embedding the operations in IPLD node that get appended as new roots of the DAG. Instead of broadcasting the operation, what I can broadcast is just the CID of the new root using PubSub. We get many good things by doing this. First, we broadcast a small piece of information. Potentially, if you hatch a huge value associated to your key, you don't necessarily need to broadcast that and make PubSub transmit that, but you can just broadcast the CID. Second, our operations are all linked to the previous operations in the Merkle DAG, which means all the operations that you know of. So when someone receives the CID, they have direct pointers to everything that came before that if they need them. Third, we have a notion of order because I'm adding new roots to my Merkle DAG. We know that this parent came later as the children, right? Because it happened later. It must be an event that has happened later because I added it on top of the children. The state, the whole state, is uniquely identified by this potential root CID and fully rebuildable by traversing the DAG and applying the operations that are contained in it. But most importantly, the state is now a set of IPLD nodes. So this is IPFS favorite food, and now we have what is essentially an IPFS powered state. We can move it using IPFS. So when a replica receives a broadcast, it can fetch the CID via IPFS as long as it doesn't already have it, which is already trivial to check because a CID will only represent one thing and not several, and then traverse the DAG from there until it reaches a child that is already known, applying the operations to the CRDT state, adding elements and tombstones to the tables as we showed before. The replica then remembers the received CID as the new DAG head or the new root of the DAG, and whenever it wants to issue a new operation, it would just add it on the top. Note that in a system with many replicas that are writing at the same time to this Merkle DAG, this is not going to make a linear blockchain with one branch that is just growing on top of each other. This is going to make a DAG with many branches, with many roots in the first place. And of course, when you have many roots and you want to add a new one, you add one on top of all of them. So the children of that will be all of them. At the same time, each replica is going to be adding their new nodes on top of the different set of branch, depending on how they're synced with them, when they learn them, on how they're doing traversing the state. And to a certain level, this is not bad. Why? Because if you have a DAG with many branches, you can parallelize traversal of that DAG. If you had a DAG with one branch, you have to go node by node. If you have several branches, the moment I have 10 children, I can have 10 workers processing those children. So as long as it doesn't get too bad, this is not bad per se. This actually speeds things up. And so with these foundations, we have built a castle. So the tower is very straight, it's solid. The system can deal with a lot of crap, replicas disappearing, rejoining, messages lost, etc., etc. But it's not that it wasn't too difficult to do this with the things and the foundations that I got from the IPFS stack. It's that all the things that I didn't have to do that matter. Did I have to build a network stack or define a protocol for my CRDT nodes to communicate between them? No, like libp2p nodes and IPFS node do that. Did I have to implement scalable strategies to broadcast the information to the network? I have gossips that it was already done for me. Did I have to implement operation tracking logic to identify replicas that are missing operations so that I can resend them to them? No. I can just, if there is no activity, I can just rebroadcast the current Merkle DAG route every minute and be done. Did I have to implement logic about which replica is the best suited to send operations to another replica that has to receive them? No, BitSwap figures that out and content routing. Did I have to add any logic to retry fetching on a different replica if the one I was copy operations from doesn't provide them anymore? No, again, like BitSwap and the DAG syncer will take care of that. Did I need to implement a linked data structure that is content address? No, everything IPLD out of the box. Do I need to care about how many replicas there are and how to connect them? No, libp2p just connects things and you can start broadcasting on the network. Do I need to worry about my system stopping if more than half of my nodes are gone, or do I have any imposements on that sense? Not at all. I don't really care. I think can die and things can join. So you see where I'm going. There are so many things done for me that are real obstacles if you're building these sort of distributed systems. And IPLD, IPFS, PubSub, they took a lot of the work that I could instead put into building the actual application on top, into actual putting things on top of the CRDTs. So Merkle-CRDTs are fantastic, aren't they? But so there are also a number of downsides, or I wouldn't say issues, but you have to be aware when you're working with these sort of systems of the trade-offs that you make. And of course, I told you like a very nice list of properties that I have. And if you want something else, you will have to start compromising on those initial properties, so it may be acceptable or not. First, it is difficult to traverse Merkle DAGs efficiently in such system. So it is a bit more complex than I showed. So pruning traverse branches and picking right the new heads when you get a fetch error as you're traversing, and ensuring that exploration of all branches happens and that you leave nothing behind even when you face errors. It's tricky. It can be inefficient. And you certainly, if you want to operate at scale, you cannot go with a very damp implementation of these things. The problem is that the issues that happen are hard to see because an issue, everything in a CRDT, everything converges. So the result may be perfectly fine, but maybe to get that result, you're working 100 times more than you should because you made a bug in your code. And so that prevents you from working at a scale. It's very hard to test, et cetera, et cetera. The underlying storage, so the underlying key value store that is holding the tables that I showed you before locally in every node, is also very important, how it is implemented, and it's going to affect performance. So there is that problem, right? Things are not as easy as I will show you in the presentation, definitely. Who knows the author of this painting? No one? Who knows the author of this painting? Mondrian, yes. Same guy. Who will tell? It's amazing. Why did I put it there? Because, well, there's a trade-off in how he was working and where he went. Obviously, in order to get into abstract geometry, he had to drop a lot of the things that he had before in his painting, so I found that interesting, and I built a comparison with that for the sake of the talk. Anyway, ever-growing DAG size. I told you we're building a Merkle DAG, and we're always adding new roots on top of it. That means it's perpetually growing. There is no compaction or snapshotting possible without compromising on some of the features that I told you before. For example, if we want to keep the part that anyone can join anytime whatsoever, and that there can be network partitions that are indefinitely lasting, and that when they disappear, everything will converge. If I want to keep those two properties, I personally cannot find a way to do a snapshotting or do compaction of the state. This is because the system has no way to agree on anything, and essentially the replicas cannot agree on a place where a snapshot should happen. So they don't know when they should get rid of the underlying Merkle DAG and compact or anything like that. Having that requires building agreement. And building agreement requires consensus. And consensus usually requires blockchain or knowing the number of participants, knowing the number of replicas, so that they can, you can send a proposals and they can accept it and so on. You cannot build consensus if you don't know who you have to talk to it about it, right? And if you introduce that, you lose the property that anyone can join at any time. And anyone that you did not know that was there because was under a network partition that you didn't see can join at any time. You can assume, you have to break that assumption and say, okay, I will not have network partitions, and I will at a certain point in time know exactly who is part of my replica set. So every application must decide if it's worth to trade those assumptions for additional functionality. But what makes Merkle-CRDTs so special is precisely having those assumptions. So if you start stepping away from those assumptions, then Merkle-CRDTs start being less special and more like any other distributed key-value store that you can build. Another issue is how to protect against dishonest actors. To illustrate, Crusaders entering and sacking Constantinople, which was Christian too at that time, so I would consider that a bit dishonest. You can put a lot of rules on what valid CRDT operations that on the CRDT operations that the system accepts. So you can put a lot of rules on what would be a valid operation and have nodes not accept invalid operations. But there is no agreement again. So you cannot have update rules to the state that are based on the state itself. So you cannot implement a cryptocurrency with wallets and balances just using Merkle-CRDTs, because the system cannot possibly agree on what is the current balance of a wallet. Maybe the balance hasn't converged. Therefore, you cannot put a rule that an update to that balance you cannot put rules on that because you have no agreement on the state. In particularly, note that updating the balance of a wallet is not a commutative operation. The order clearly matters. Therefore, this is not directly compatible with Merkle-CRDTs or even with CRDTs in general, I would say. In general, I find that there are adversary scenarios that are very hard to deal with when working in CRDT land. And the rules that you can set are limited by design and by how data type works. Therefore, normally, Merkle-CRDTs would be used in trusted systems where you trust your replicas to behave properly, or you will interleave them with actual consensus systems or things that give you a bit more guarantees on and protections against bad actors. Finally, there's a question of latency. Batching updates can give you a huge performance boost. It's going to save space because you have to issue less IPLD nodes. Instead of one operation per node, you can put 9,000. It's going to reduce network congestion because you don't have to broadcast so many updates. But of course, it introduces latency by the time that you spend building the batch and receiving the operations that make the batch. Will be a time that the other replicas are not receiving the keys that are being written, etc., etc. So applications that want really low latency, so it's really important that they get a new key very soon. Perhaps they don't have time to wait for 1 minute for a batch to be completed. But others can certainly take advantage of this. Who knows what's happening on that picture? It's someone someone opting for a high latency, low throughput link. Some boats are being sent over a mountain. Boats are not made to drive over mountains. This is actually what happened when the Turks conquered Constantinople. There was a water blockade, and Mehmet II decided to essentially do that with his boats to attack from the other side. And it surprisingly worked. If you have a chance to read about the fall of Constantinople, do, because it's just fucking nuts. So what is this all for? It's a complex world. There is good and evil, and there are different applications, and there's never one fit-all solution. Some of them are weirder than others, but in the end, there might be an application to which this is relevant or partially relevant. The paper that we wrote happened in the first place. We were looking how to painlessly sync the pinset database in IPFS clusters using the Go IPFS stack. So OrbitDB was already there. So OrbitDB is a database written in JavaScript by one of my co-authors, by Samuli. And it was already using these principles, right? So in cluster, we have Raft before, and Raft is awesome. It's very optimized. It works very well, but Raft clusters cannot operate if half of the peers are down. So that was bad, because if you have a 2-node cluster, it just cannot operate if one peer is down. So that was like a huge pain in the ass and a usability problem. And every node that you wanted to add had to be acknowledged by all the other nodes. Every departure had to be acknowledged by all the other nodes. If one node left, it was errors everywhere. And every update that you wanted to send to the cluster needed to travel through the leader. So not everyone could write, only the leader could write at every time, which means redirecting everything to the leader, etc., etc. It was not really suited to the kind of flexible system that we wanted to do with cluster. Therefore, we implemented our pinset syncing layer with Merkle-CRDTs. And we have proven that the Merkle-CRDT data store that powers cluster can scale now to 100 million keys and 100 million objects on top of what is now a pretty big Merkle DAG, because it's been growing for a year. Using batching, we can, at the very, very, very least, so using a very stupid approach to sending updates to the API, we can sync more than 250 objects per second. You can do more. You can hit several nodes, or you can parallelize your request to the same API and so on, and get more items per batch if you want, but this is like the most stupid approach and the base number that I can give you. The setup is highly scalable, and the system can absorb write peaks very naturally, because you just write, you can build on top of your Merkle DAG, and you broadcast as you want, and the system will sync as the conditions in the system allow. That means as bandwidth is available and as CPU is available, the things will travel around. We can add new peers. We can turn off peers for maintenance without having to worry about any errors or any issues in any of the other cluster peers. So this is not at all theoretical. We wrote all this code, and we're really using this castle. In any case, as I said, the purpose of this talk was to give you not only the overview of how Merkle-CRDTs work, but ideas on how you can build your own castles using the strong foundations on the IPFS stack and ecosystem. I hope you enjoyed it. Thank you very much.